So we're now ready to draw the shear bending moment diagram after having figured out what the reactions are. I've replaced my reactions with their actual magnitudes, and I've left the directions intact because they were correct the first time around. I've dropped down lines every time there is a distinctive point load, a real point load. Notice how I didn't for this, because that's not a real point load. That's fictitious, it's virtual. It's easier to turn this distributed load into a point load to find reactions. However, this is the real load on it, on the beam. So I've dropped down 2 lines. I've done a line for my shear diagram, bending moment diagram. And I've labeled it already. That way I don't forget. Shear diagram, V is typically the convention for it. Units, what a positive shear looks like, max, min. Ditto for the bending moment diagram. Units, what a positive moment looks like, max, min. And now I'm ready. So first things first, shear diagram. I go left to right, starting at the leftmost point. At this location here, I start at 0. And then I go up or down by whatever shear inducing force I have. At A, I have 9.85 going up. So that's what I do. Okay. And now I have to move to the next shear point, or the next point where there's a shear force, or a force that's inducing a change in shear. So the only other one that I see is this one here, but how do I get from there to there? Well, I must reduce this value of shear by this value of the distributed load. And this one basically says that for every foot we go this way, we go down by 2 kips, because it's the slope of that straight line. So if I go over by 8 feet, that means I go down by 16 kips per foot. Okay? So if I do this 9.85 minus the product of these 2 numbers, 16, I'll get to down here. And if we've done things correctly, that number should match this. Okay? And then I connect these 2 points with a straight line. Now, I'm freehanding this, but you're expected to use a straight edge to draw it. If you don't, you'll get a 0 on this. Okay? No freehand straight edges. Okay? And then, what do I have here? I have a force that goes up by 6.15, which is great because it brings me to 0. Okay? Now, a reminder again, how did I get here? I did 9.85 minus, because this is going down, the product of these 2, right, which is the slope and the distance. So that's 16, and that brings us down to there. Okay, okay, how do we get to the bending moment diagram? That's too soon. We have to finish marking this up. What is the maximum shear? 9.85. What is the minimum shear? Minus 6.15. Okay, to get to the bending moment diagram, the key word is area. Remember that? As long as we can find the areas of all the shapes that appear in the shear diagram, we can do the bending moment. So let's do that. I identify 2 areas here. Okay? There's this area 1 right here, and this area 2 right there. I also remind myself that area 1 is going to be positive, because all the dimensions are positive, and area 2 is going to be negative, because this dimension, that height, is negative. Also, remember from in class, wherever the shear diagram passes through the beam, we have to drop another line there, because it's something special for the bending moment. Okay? So, in order to define this area, it's a triangle. So we need this dimension and that dimension. This dimension here, we can call it x1. Okay? And if we remember that this line is represented by this slope, and we know that this number, the rise, is that value there. If we do rise over run and rearrange it, we can get that value there, which is the run. So let me write it over here. x1 is equal to 9.85 kip divided by 2 kip per foot. Okay. So when you divide those two numbers, that answer is going to be in feet. Okay. And that value is 4.925 feet. Now that we know that, we can calculate area 1. And don't forget, for a triangle, you must divide by 2. That's a very common, silly mistake to make where you could potentially lose marks. That area comes out to be, let me just calculate it. Wow. $24.256. Okay. Now, if we know this is 8 feet, and we have x1, are we able to find what the value of x2 is? Certainly. It's the difference between the two. So that comes out to be 3.175. Oh, so close, not quite. 3.075. Area 2 is minus 6.15 kips times that distance. And don't forget to divide it by 2. This area comes out to be 9.456. Okay? So we're going to pause here for a second.